All right, so last week we finished up with the mechanism, rate equation, stereochemistry, electrophile analysis, and nucleophile analysis for both Sn1 and Sn2 reactions. This overview sheet comes in handy. One thing I would say is don't try to brute force memorize it. Try to understand why we filled in those boxes. That's the key thing I want you guys to take away from this chapter is the why aspect. At the bottom here, I've got some really funny videos, so I want to give you guys a chance to watch these that visually describe the difference between Sn1 and Sn2. So let's take a look at Sn2 first. This is from the University of Surrey.
Primary halogenoalkanes undergo Sn2 reactions, where the S denotes a substitution reaction, the N shows the reaction involves a nucleophile, 2 is the number of species involved in the slowest rate-determining step. A nucleophile is an electron pair donor. It is attracted towards species carrying a full or partial positive charge, with which it can form a dative covalent bond. Consider the reaction between a hydroxide ion in solution and bromoethane. Both reactants are involved in determining the rate of the reaction in a one-step process. The hydroxide ion attacks the carbon atom from the opposite side to the halogen atom, because the bromine atom A is so large it impedes the approach of the smaller hydroxide ion, and B, it repels the negative charge nucleophile. The lone electron pair on the nucleophile forms a new dative covalent bond with the partially charged carbon atom to give an unstable transition state complex. The complex behaves like an umbrella blowing inside out as the bonds rearrange into a tetrahedral structure. A bromide ion, called the leaving group, is released. The transition state complex.
All right. So I think that does a pretty good job of showing that
Alkanes.
transition state. That's the trigonal bipyramidal transition state. Oh yeah, go for it. All right, so let's take a look at the video for Sn1 and see how that compares again. What's the main difference again before we look at it? It's a two-step process. What's the intermediate that we go through? Carbocation, right? So let's take a look at what this looks like using their same kind of goofy videos.
Tertiary halogenoalkanes undergo Sn1 reactions, where S indicates a substitution reaction is occurring, N indicates that a nucleophile is involved, and 1 indicates that only one species is involved in the slowest rate-determining step. In tertiary halogenoalkanes, the small hydrogen atoms in primary halogenoalkanes are replaced by bulkier alkyl groups. Tertiary halogenoalkane. The bulky alkyl groups do not allow attacking species to approach the central carbon atom. Consider the reaction between 2-methyl-2-bromopropane and a hydroxide ion. It has a two-step enthalpy profile. The first step, the heterolytic fission of the carbon-bromine bond, has a high activation energy, EA1, and therefore determines the rate of the reaction. The first step involves only the halogenoalkane and proceeds via a transition state complex to form a carbocation. The second step has a much lower activation energy, EA2, and hence is considerably faster than the first step. The carbocation reacts with the nucleophilic hydroxide ion via a second transition state to form the product 2-methyl-propan-2-ol. transition state, carbocation, EA2, Sn1 Reactions.
All right, enough with the cheesy videos. I like them because I feel like they help you really visualize what's occurring when you're making and breaking those bonds. And it's important to remember, especially with the Sn1, that you're going through that trigonal planar carbocation where you can attack from either face. And they don't quite mention it in the video, but it's important to remember that it is a planar compound. All right, so last week we finished up talking about nucleophiles. We said that the nucleophiles are better if they're not bulky and they're better if they're unstable. So let's go back and talk about that a bit more. And we gave two examples last week. We had one with a bulky electrophile versus a non-bulky electrophile, and we said the non-bulky electrophile is better because it has an easier time approaching the electrophile. And then in example 2, we said that the less stable nucleophile, meaning the one that's more in the smaller atomic radius, is going to be the better nucleophile. And this is really similar to acid-base activity, right? So let's take a look at a few other examples too. So for the first one, let's do this. Which is better? Nucleophile. And I'll give you guys a pair, and I want you guys to help me pick. So hydroxide versus NH2 minus will be the first one. Then we'll do water versus ammonia. And then we'll do water versus hydroxide. All right, for the first one, which is going to be the better nucleophile, hydroxide or NH2 minus? NH2 minus, why is that? What's that? So NH2 minus you think is going to be the better nucleophile, why? Anybody want to share? What do you think? You think OH is going to be better? All right, let's think about it this way, right? They're in the same row in the periodic table. When we're looking at rows in the periodic table, are we looking at comparing atomic size or electronegativity? Electronegativity. All right. Which one's more electronegative? The oxygen, which means it's more stable with the negative charge. That means that this is a better nucleophile. It is less electronegative and less stable with a negative charge. Does that make sense? So we're really looking at stability. All right, let's think about the next one. The next one's getting a little bit more abstract. Which is going to be the better nucleophile, water or ammonia, and why? All right, let's think about it, right? They can each act as a nucleophile because they have lone pairs. Which one's going to hang on to its lone pairs more tightly? The oxygen, right? So its lone pairs are being held a lot closer. That means they're going to be less available for nucleophilic attack. So again, ammonia is going to be the better nucleophile. Since its lone pairs are held less tightly. All right, and then the last one, which is going to be the better nucleophile? Water or hydroxide? Hydroxide, right? Because it's got a charge, it's going to be a lot less stable. All right, and then just to give a plug to this website, the Master Organic Chemistry website has a really good summary of what makes a good nucleophile. And one of the things he ends on is talking about the solvent. And the solvent plays a critical role in how nucleophilic something is. So we're going to talk about that next. So let's do this. Comparing atoms in the same column depends on the solvent. So let's continue along that train of thought and then create a list of solvents that can be used in these substitution reactions. All right, so in organic chemistry, we have a handful of common solvents that we use, and we try to break them apart into three general groups. The first one are polar protic solvents, and what does it mean if you're protic? What's special about all of these that the other ones don't have? Think about intermolecular forces. Yeah, they can all H-bond, right? So these are H-bonding solvents. There are some cases where we may want to use hydrogen bonding solvents. Polar aprotic solvents, on the other hand, are non-H bonding. Nope, this was handed out a while ago with the common bases and solvents, so non-H bonding. If you need an extra copy, it's on the class website, but polar. And then down here we just have non-polar, non-H bonding. Typically, when we're doing these reactions, we want to use a polar solvent, and we'll talk about why in a second. So we're going to be using one of the solvents from these first two rows up here. Okay, so let's take a look at the solvents. And in order to do this, we really have to consider the transition states. Oop, let me do this in black. So I'm going to abbreviate transition state as TS double dagger for Sn1 and Sn2. All right, so Sn2 we've got over here. How many humps should Sn2 have for its reaction coordinate diagram? One hump. So we'll have energy over here. We'll have reaction over here. We know we've got starting material going to product down here. And we've got this activation energy. Okay, so let's draw the transition state for just a generic reaction, and I'm going to do this in blue. So we know we have the nucleophile attacking a carbon, so it's half made. In this case, I'm going to do a methyl group. Oop. And I'm going to just have two hydrogens down here, and then over here, I'm going to have my leaving group falling off. It's important to remember, too, that we have partial charges. Where will the partial charges go for this transition state? Yeah, the nucleophile and the leaving group, because they're popping off, will have a partial charge. So I'm going to draw that with a delta negative, delta negative. And then I'm going to bracket everything here to show that this isn't a compound you can isolate. It's just a transition state. Okay, let's do the same thing for Sn1. And we're going to focus on the rate determining step. So the rate determining step, if you remember, is going to be that leaving group falling off. And then we're going to have your nucleophile attack into the carbocation. So EA1 is our rate limiting step. And same thing here. We're going to show the activation or the transition state. And I'm just going to draw three R groups coming off this carbon. And our leaving group is falling off. Same thing here. Our leaving group is going to be a delta negative, but in this case, our carbon is going to become more positive, so I'll show a delta positive for that transition state. It's important to note, though, that each of these transition states goes through a polarized or partial charged transition state, right? Where you have delta positives or delta negatives. So both reactions go through a polarized transition state, meaning they have a partial positive or partial negative. And polar solvents help stabilize this. That means that substitution reactions are faster in polar solvents. The other thing too is quite often it has to do with solubility, right? If you're trying to dissolve an ion, like we've seen in some of our example problems, it's going to be more soluble in a polar solvent than a nonpolar solvent, right? Nonpolar solvents tend not to dissolve ions very well. So it's both practicality and we're trying to lower that activation energy that we have to overcome for these reactions. So that's the first one. Now what we need to do is compare the polar protic solvents to the polar aprotic solvents. So let's come up with a comparison. Versus polar aprotic. Okay, and what I'm going to do is I'm going to have two nucleophiles, and right here we know that this nucleophile is going to be this negatively charged sphere. I'm just going to do generic Nu. It could be any sort of nucleophile. And let's do polar protic on the left. And for polar protic compounds, these are stabilized. So I'm going to use a common polar protic solvent, which is just water. And it makes sense because in this case you can hydrogen bond to your nucleophile, right? So let's make some notes. A nucleophile can H bond to the solvent. Does that mean that the nucleophile is going to be a better nucleophile or a worse nucleophile if it's hydrogen bonding to the solvent around it? What do you guys think? Worse, right? Because it's held tightly by the solvent. The solvent really, really wants to interact with it. It's not going to let go of it as easily. This results in the nucleophile being weaker. So if this is the case, would we want to use a polar protic solvent in an Sn2 reaction or an Sn1 reaction? What do you guys think? Which reaction does the nucleophile matter more in? Sn2, the nucleophile matters more. So in this case, would we want to use a polar protic solvent for an Sn2 reaction? No, in fact, it's the opposite. It's not good for Sn2, where nucleophile strength matters. Okay, on the other hand, let's come up with polar aprotic. In this case, we've got a nucleophile, again, with the negative charge, and I'm just going to choose acetone this time. Kind of looks like the acetone's sitting on the nucleophile. Why do I have it oriented that way? Yeah, the partial positive of each of these acetone molecules is going to be facing that nucleophile. So all of these acetone molecules are going to orient them so that that delta positive is closer to that nucleophile side. So it's a weaker interaction, but it is still an interaction where they surround the nucleophile. But let's make some notes. The nucleophile is less tightly held. /solvated. That means that this is more nucleophilic. Philic. And this is better for Sn2. Does that make sense? It's a little bit weird to think about, but in this case, we don't want our nucleophile to hydrogen bond with the solvent because that stabilizes our nucleophile. We want a less stable nucleophile. Yep?
Polar Protic, not good for SN2.
All right, thank you. I'm sorry if I make spelling errors. Sometimes I write fast and I'm speaking, so it makes it a little hard to keep up. Okay, so another way of thinking about this, right, is let's make two different reaction pathways. Again, we've got energy down here. We've got reaction over here. Our polar protic pathway I'm going to do in black. Our polar aprotic pathway is in blue. Oh, let me clean this up. And this blue activation energy is going to be a lot lower than this black activation energy shown here, simply because we are destabilizing the nucleophile. Make sense? So we have the lower energetic barrier that we have to overcome. So it really has to do with how tightly that solvent's wrapping up your nucleophile. The more it interacts with the solvent, the lower this energy is going to be, and the larger the hump is that you have to overcome for that reaction. Does that make sense? So then the question becomes, well, why would you ever use a polar protic solvent in a substitution reaction? Well, maybe we need to consider Sn1 reactions where the nucleophiles don't matter as much, right? So let's consider Sn1 reactions. So Sn1 reactions, we know the nucleophile, whoa. Come on. We know in Sn1 reactions that the nucleophile strength doesn't matter. What does matter for an Sn1 reaction? What's the rate limiting step involved? Loss of the leaving group. Rate is determined by loss of leaving group. All right, so let's think about it this way. The transition state that we're trying to stabilize in this case, I'm going to redraw it down here. It's going to be something where the leaving group is falling off. So this will be delta negative. This carbon will be delta positive. And this is our transition state. But in this case, we want a solvent that will stabilize this leaving group falling off. Okay, so which solvent stabilizes negative charges or partial negative charges better? What do you guys think? The protic ones, right? Protic solvents can hydrogen bond to that partial negative and help it as it gets ripped off of that molecule. So let's make a note of that. So polar protic solvents can H-bond to leaving group as it falls off. Which stabilizes the transition state. So again, we can think about this from a reaction coordinate diagram point of view, where in this case, we're not doing anything to the starting materials. The starting materials are about the same, but what we are doing is lowering that activation energy by stabilizing the transition state. So let's briefly draw that. So same thing here, I'll do polar protic. And then over here, I'll put polar aprotic. And we know for SN1 that we go through this intermediate, then we've got a second hump as we go to product. Where with the polar aprotic solvent, everything looks the same. Except this one has a much, much larger activation energy for the polar protic solvent than we do for, let me do it in black so it's the same, than we do for the polar protic. So really what we're doing is we're ultimately trying to lower the activation energy for our rate determining step. And there's two ways of doing that. We can either stabilize the transition state or we can destabilize our starting material. They both accomplish the same end goal. But you need to be very careful with which solvent you use for which reaction. So let's make a simple note and talk about this. Polar protic is better for SN1. Polar aprotic is better for SN2. Does that make sense? It's a little bit abstract to think about it, but I want you guys to really understand the why behind these things and not just brute force memorize polar aprotic is for this. All right, so now what we need to do is analyze our nucleophile strength a bit more for SN2 reactions because it does get a little bit nuanced. If you notice, I said is better is not the only option, right? So you can use polar protic solvents for SN2, but the rate's going to be a little bit slower, and I'll show you guys some tricks that you can use. So let's go into nucleophile strength a bit more. ... All right, so let's do this. I'm going to compare nucleophile strength in the same column. So an example of this could be hydroxide. If we go down the column below oxygen, we have sulfur. If you go below sulfur, we would have selenium. So we've got a nice column of different nucleophiles that all are in that same group, right? All right, so if we think about it, which is going to be the most basic? Is it going to be hydroxide at the top or the selenium compound at the bottom? So basicity, right? Going back a little bit. So does it get more basic as we go up or more basic as we go down? And why? More basic as we go up, right? Why is it more stable as we go down? Yeah, we've got a negative charge over a really big atom, right? So if we think about it, we know that it's more basic as we go up a column. And then we have to consider hydrogen bonding, right? So let's say we're in a polar protic solvent. H bonding can occur. All right, which of these will H bond the best with a hydrogen bonding solvent? The hydroxide or the selenium? Okay, so more H bonding as you go up that column. All right, so knowing that, which one's going to be more nucleophilic in a polar protic solvent? Will it be the top or the bottom? What was that? The bottom, why? Yeah, less H bonding, right? We know our nucleophile shouldn't be H bonding as tightly, so this would be more nucleophilic. in a Protic solvent due to less H bonding strength. Does that make sense? So let's make a little note on this, and this does get a little abstract, but it will make sense when we see the counter argument. In Protic solvents, nucleophiles with a negative charge get stronger as you go down a column. All right, now let's do the same thing, but we're going to do it a little bit differently. We're going to think about aprotic solvents. All right, so same exact argument. I'm going to have hydroxide up here. I'm going to have the sulfur analog down here, and I'm going to have the selenium analog down here. We already said that it's more basic as we go up. And aprotic solvents don't H-bond. So which of these do you think will be the most nucleophilic now? OH, right? So let's make a note of this. In polar aprotic solvents, nucleophiles with a negative charge are more nucleophilic as you go up a column. Does that make sense? So it really depends. If you want hydroxide to outcompete the sulfur analog, maybe you should use an aprotic solvent, but if you want your sulfur analog to outcompete hydroxide, maybe you want to use a polar protic solvent. So you can actually switch the nucleophile strength depending on which solvent you're planning on using, right? It's a little abstract to think about. All right, so let's consider another example. All of the nucleophiles I've shown so far are negatively charged. What happens if we've got a neutral nucleophile? So what about nucleophiles without a charge? So let's compare these. I've got ethanol over here, and I've got the sulfur analog over here. Which of these do you think is going to be the better nucleophile, and why? I'll give you guys a minute to think about this, but check with your neighbor. Does anybody have an idea so far? Anybody in the back? What do you guys notice about the two compounds here? Are they polar protic or polar aprotic? What do you guys think? Yeah, they both look polar protic to me, right? They both have a hydrogen coming off an electronegative atom. All right, so knowing that one, which one's going to pack more tightly with itself? Probably the one that can H-bond, right? So this can H-bond. That means that it is tightly packed with itself. Another way of thinking about it, right, is we know H-bonding molecules are sticky, so these are all sticking to one another. That means that this is less nucleophilic. Over here, this can't H bond. That means it packs less tightly. That means that it's a better nucleophile. So if you have an uncharged species, so for uncharged nucleophiles, they get better as you go down a column. So we do have three different things we've got to keep track of. We have to keep track of whether or not our nucleophile is charged. If it is charged, then we have to consider whether or not our solvent's protic or aprotic. If it's not charged, the solvent doesn't matter as much. We know that it gets better as you go down a column. So that's a simple thing you can use to keep track of it. All right, one last thing before we continue on is this trick that we use oftentimes for Sn1 reactions. In Sn1 reactions, your solvent is often your nucleophile. It just makes things a lot simpler in terms of reaction cleanup. There's less to add, less things to throw out at the end. So let's consider the following reaction. All right, I've got an iodine right here, and I've got a methyl group right here, and then I've got methanol over here. All right, do you guys think that this is going to be an Sn1 reaction or an Sn2 reaction? Sn1? Okay, so I think Sn1 too. That means the leaving group will fall off first. And I'm going to show this with equilibrium arrows. Okay, and then we've got this methanol floating around. Whoop. And we've got our iodide that fell off. Why did I show this with equilibrium arrows? Yeah, the iodine could theoretically attack back in and we could go the opposite direction. So you can show this with equilibrium arrows. All right, if the iodine attacks back in, we're not making forward progress. So what will our other nucleophile likely be? Yeah, the oxygen. So the oxygen we know can attack from the top face or bottom face. Does it matter for this problem? Well, let's try it, right? So for one of these, I'll do the bottom face. And then we'll do the top face for the next one. What's the relationship between these? Are they enantiomers? This would be a good trick question for an exam. Now I can't use it. Are they enantiomers? So enantiomers means we flipped all of our stereocenters. Do we truly have a stereocenter? No, there are no stereocenters in this molecule, right? So these are identical compounds, so we only have to draw one of them. You don't have to draw it twice. So these are identical. So I only need to draw once. All right, and then we also have this iodide floating around. And let's assume we've got excess methanol. Whoop. Okay, which is going to be the better base, the methanol or the iodide? What do you guys think? So if you go to a pKa table, you'll actually find out that hydroiodic acid is stronger than hydronium. So hydroiodic acid is a really, really strong acid. That means that iodide is a really, really crummy base. So in this next step, it's more likely that your methanol is going to grab this proton. And I'm going to show our equilibrium arrows. And now we would have our methyl group sticking up. It doesn't really matter if you draw it with dashes or wedges at this point because it doesn't have a stereocenter. We have our protonated methanol, and we have our iodide as a negative charge. So quite often with Sn1 reactions, we have to show more than that intermediate step. We have to, in addition, show proton transfer as your last step. Does that make sense? This is really similar to your problem of the day, and I noticed a lot of you drew I- grabbing that proton. I personally don't care. Just show that final proton transfer to get to your neutral product. Does that make sense? All right, so for the pod tomorrow, what I want you guys to do is to start thinking about the leaving group a bit more. And like I said, it's closely related to acid-base chemistry. So if you are confused, maybe go back and review some of those acid-base notes.
Is this H with a positive charge or not?
Oh, that should be H2OCH3. So it's got 2 protons coming off of it. All right, good luck studying. If you guys